Good afternoon, everyone. Welcome to the technical talk today. We have the pleasure of having Dr. Rostami joining us for the talk. So a pleasure to welcome you all. This specific talk is special to us because it's not only the first out of a series of talks that is going to be offered by the ARMA's, American Rock Mechanics Association's Technical Committee on Tunneling, but also is an event that's co-hosted by our student chapters here at Mines. We have the ARMA's student chapter at Mines, as well as the Underground Construction Association of SME student chapter that have helped with advertising and coordinating this event. So the plan would be as follows. We would have a presentation for about 40 minutes, followed by up to 20 minutes of questions and answers. Please feel free to post your questions at any given time using the chat option that you have available at the bottom of your screen, but also make sure that you mute the microphone and be on the listen-only mode. So we can then hear from you or go through the questions as part of the question and answer period. For those who are attending this webinar either virtually or in person, we have the option of issuing a professional development hour certificate upon request. So please contact our professional development office at learn@mines.edu if you're interested in receiving a certificate for your participation in this session. Today's talk is offered by Dr. Jamal Rostami, who is a professor of mining engineering here at Colorado School of Mines. Dr. Rostami holds the Haddon Alacer Gold Endowed Chair position and also serves as the director of the Excavation Engineering and Earth Mechanics Institute at Mines. Dr. Rostami received both his master's and PhD degrees in mining engineering from Mines and has had over 30 years of experience in design, management, research, and teaching in the field of mining, tunneling, and underground construction. So Dr. Rostami, please proceed with your presentation.
Well, good afternoon, everyone. Thanks for joining in. And I might as well give a shout out to Professor Adayat, the chair of the ARMA Tunneling Committee, for coordinating this meeting. This is the first of a series of webinars that this committee will be offering throughout the year. So I invite everybody to look it up and join, and of course our own UCT group, our esteemed student chapters for ARMA and UCT. Thanks for coordination and thanks for bringing the munchies for those who are participants. So enjoy your lunch while you're listening, and I might have to, shout out because I want to make sure that the recording is correct for those who are joining online and also those who might be listening in later. Well, I'm muted on one system. We are actually, the microphone doesn't work on the desktop, so we are going with the microphone on the laptop. That's why I have to get closer to the laptop. Apologize for that. Hopefully we'll get over it. All right. The topic that I wanted to talk about is about, the lessons learned on the claims that have come across in tunneling world, especially for tunnel boring. So essentially, talk about what makes tunneling very special, and especially coming to the issue of geotech investigation. We'll discuss some of the issues that we have encountered relative to hard rock, talk about weak and jointed rock and what the issues are and what the typical claim situations are for jointed rock. Of course, water has been chasing miners and tunnelers from the beginning of time, and it is consistently an issue there. And I'd like to touch upon that issue of boulders. Boulders are made of rock, but they're in the matrix of soil, and they're the worst of things that we can encounter in tunneling, especially with TBM. So diving right in, essentially, why are we talking about this? Why is this issue important? If you look at the world of tunneling and contracts, about 90% of contracts in tunneling end up in claim of some sort, one way or the other. Could be a change order, it could be actually construction claim relative to differing site conditions. So differing site condition is the term that I'm going to use, DSC. So if you hear me saying DSC, that's what it means, differing site condition. And what it refers to is that the contractor comes in, starts the tunneling, and something happens, and essentially they can go to the contract clause and say the site is different than what I was told. It's different than the geotech investigation reports and geotech baseline report. And that is a basis for claiming and getting compensated, right? So this DSC is a major issue in the world of tunneling. Why is it happening so frequently? It's because we have an incision, a borehole here, a borehole another couple of 100 meters away, and so on and so forth, sometimes a couple of kilometers before we have any information. And it's left up to interpretation of what is happening between the two. And the difference here is that in a typical construction, as long as your foundation is okay and you find out what's going on with the foundation, you build upon and you're done, right? So your interface with ground in a typical construction is with the foundation. As long as you can figure it out, you're good. The difference in the tunneling is that the entire structure is in the ground. If it is 5, 10, 20 kilometers, you're dealing with 20 kilometers worth of varying ground conditions, right? And you have to quantify it, and sometimes you don't have the borings to do it. So it actually opens up the possibility for claims. Of course, different parties interpret the situations differently, and when it comes to strength of the rock, joint condition, and water, you have an array of different interpretations. Although the industry has tried to address it by advocating geotechnical baseline report, which essentially looks at the information and sets up a baseline for all the contractors, but still there is some room for interpretation. And the key takeaway that I will reemphasize is that you have to look at the consequences of each of these situations before you can come up with the right way of addressing it in your geotech investigation. So the first construction claim I got involved with was actually in early 1990s. I started working at EMI, and there was a project going on in Colorado Springs, for a water tunnel, Twin Peaks tunnel, and TBM was small, and the rock is typically granitic, but it's pegmatite. It's very coarse-grained Twin Peaks pegmatite. And the claim was on low penetration rate on the machine. We brought some large samples from the site here at EMI. We tested, linear cutting test. And, we recorded the forces. And what we found out was that the forces on the disc cutters for cutting of the rock of the TBM in pegmatite and coarse grain granites was different than a typical medium grain or low grain granite. That was not actually reflected in the unconfined compressive strength, which was quite an interesting situation. So higher forces means lower penetration by the TBM. And guess what? That was the differing site condition there. These are the pictures and actually drawing of the linear cutting machine and, surface of the rock in our testing at EMI. A follow-up project was the Boston Outfall project. This is a project where they sink a shaft, they go under the ocean in Deer Island and collect all the sewer from the Boston area and pump it into this outfall, and it gets diffused in the water stream in the ocean. So it's a 10-mile project, 10-mile long tunnel, 26-foot diameter, roughly 7 or so meter diameter. Was built by Kiewit Atkinson Kenny joint venture. The geology of the area, Boston area, is primarily argillite. And not much of a depth, though, a stress situation was not that bad. But differing site condition was actually claimed because in the geotechnical interpretation or summary report, an expert had put down that estimated penetration rate should be 15 feet an hour. And what the contractor was getting was 9 feet an hour. Imagine you're planning for 15 feet an hour, you get 9 feet an hour. That's about a 60% almost less, right? Or 50-some% less. And that created a delay. And the contractor actually claimed about $54 million at the time, if I can remember correctly, for that, because they had 54 weeks of delay, $150,000 a day cost of running the site. 1 week is $1 million loss, and 50-some weeks of delay because of the low penetration, $54 million. In that same project, and that was one of the early projects where they use a double shift machine that you see in the picture here. They had a different site condition claim also for grouting, because again, remember, this is going under the ocean. Argillite, which is a high-grade siltstone sandstone, is supposed to be very tight formation, but it is leaking water. You're going under the ocean, you don't want water in your background, right? So they had to do a lot of grouting, a $70 million claim for the grouting as well. So that was the situation, and right around the same time, 1995, we got involved with this project in Queens, the Queens Tunnel, water tunnel in New York City. So the claim there was, related to formations and a Manhattan schist that is known to be in the area. The tunnel that we got involved with, the Queens Tunnel, was actually built by Kiewit Shea joint venture, a 23-foot diameter machine, say about roughly 6.5, close to 7 meter diameter, 700 feet deep, 210 meters. Again, a low penetration claim. They were getting 6 feet an hour as opposed to 9 feet an hour that had been anticipated. Again, a 30%. A slower penetration means that the project is going to get longer and the cost is going to be higher. We looked at the rock mass conditions. In this case, actually, the issue was rock mass and the frequency of joints. And the claim was actually in both ends. There were areas that the joints were less than anticipated, so the machine was going slower, right? When you have more joints, you anticipate to go faster. The joints were not there, so it was going slower, right? And there was areas that were, multitude of joints and blocks were getting loose, so the contractor with an open type machine that you see here, they had to stop and add ground support. You see how it works? So when the joints were higher than anticipated, there were a ground support claim, because the machine was going slower. When the joints were less than anticipated, right, they were claiming penetration rate. So you get it on both ends. You got to have it somehow fixed and figured out. At the same time, it was funny, it was just at the end of the other project, which was built by Shivoni Shea, another joint venture contractor, a different section of the water tunnel number 3 in New York. And they didn't have penetration rate claim, but they had a cutter change claim, because they were, the claim was revolving around, we are using more cutters than the abrasivity of the rock indicates, right? When you have more abrasive rock, the cutters were faster, so you have to inspect them more, and you have to change them more. You have to pay for the cutters and the time of change. And it impacts the utilization, meaning that your daily advance rate suffers. Against daily advance rate being lower, it means that, right, the construction time goes up, hence the claim. So you can see in a simple situation, you can run into multitude of complexities relative to the machine. The next one, Seymour Capilano project, I just put this one in because it has to do with the in situ stresses. This is the project that my tunneling class is very familiar with, because this is their base background project for the semester. So this was a twin tunnel going between a dam and a water treatment plant, 7 kilometers roughly. So there were twin tunnels, 2 tunnels. 3.8 meter diameter. The depth varied between 300 to 600 meters going under the mountain. The rock was primarily granite, beautiful, good granite, but certain section of the rock was actually weathered. However, as they moved in and the depth started picking up, you could see breakage in the formation at 5 o'clock and 11 o'clock positions, right? You're going towards the tunnel. You can imagine 12 o'clock is the roof, 6 o'clock is the floor, and you have the rib lines at 3 and 9. So 5 and 11, sort of a almost vertical, but then angle, was breaking up, and that was because of the in situ stresses. So after the fact, when we actually measured it, the factors for the horizontal stress was 2 to 3.5 times the vertical stress. So you're going under 600 meters of overburden with 2 to 3 times higher horizontal stresses, right? And imagine what's going to happen. So the 5 and 11 o'clock breakage was because the tunnel was actually being squeezed on the side. So these 2 points were actively spalling and breaking up. So in several visits to the site, we were just sitting or standing on the backup, and you could hear the ground going like breaking up. It was pretty interesting and scary. In January 2008, they had a rock burst event. So the machine in the raw water, I guess, was going ahead. There are 2 machines going simultaneously. One is ahead of the other one. The machine that was about 100, 200 meters in front of the other heading had a rock burst where they actually gently went to this weathered ground. So the in situ stresses are high. In good rock, it was holding up. It was breaking, but it was holding up. When they entered the weathered rock, the face collapsed. And the face collapse happened in January 2008. The contractor was claiming that the air blast of the burst was so, strong that it knocked out a couple of the workers in the backup of the machine. The face collapsed, area around the whole machine collapsed. And they had to recover the machine. The contractor actually stopped working, Billfinger Berger, and said, look, this is dangerous. So they actually claimed a safety clause in the Canadian labor law and saying that we cannot operate now. So they were also pushing to get the contract going from, the bid type of lump sum to, time and material. Time and material means that, okay, we'll do it, just you pay us whatever we spend the time, right? So, or cost plus in a way, that's some of the contract types, they call it cost plus, time and material or cost plus. And the owner didn't actually accept that premise and terminated the contractor. And finally, what happens is that the first contractor was terminated. They hired an intermediate contractor to maintain the job site. And then they rebid the job, and Frontier Camper went and finished the job. So what happened here is that when we looked at the geotechnical investigation, there were some discussions of high stresses in the ground early on. However, for some reason, the design engineers, not to be named, decided to ignore it. At one point forward in the 3rd or 4th revision of geotechnical baseline report, they completely eliminated the discussion of in situ stresses. And guess what? It came back to hunt them. So if it is there, if you're in an area that you anticipate high in situ stresses, take it into account. You have to essentially care for it. Because what happens is this, you can see the profile is supposed to be a circle, right? And the wall up to about a couple of meters had already collapsed and come in. This was what the roof would look like, right? It's bulging. It is actually actively crushing the roof and floor. And in the roof area, it was accumulating on the wire mesh. I mean, you could see it. It when you see something like this, you cannot just walk by and continue tunneling. You have to go cut the wire mesh, clean up that mess, set up another set of wire mesh, and do the bolting again. And imagine that bolt. What is it holding? The anchor is holding on to some part of a rock, but the rest of it is literally holding the broken ground. So you have to cut off that bolt and put the new bolts on. Let me show you this quick video. Okay, it doesn't like it. Anyway, in the video, what you see is the machine is actually cutting into the ground. And what you see here is the finger shield behind the head. So right as the machine is cutting and going in, right behind the cutter, in the finger shield area, right behind the cutter head, let's say 2 meters behind the face, the ground is crumbling and coming down. It's breaking on its own because of the stresses. That is the situation they had to deal with. Of course, if you go to some of the longer tunneling projects, like the Leuchberg Tunnel, a 57-kilometer tunnel, 151 kilometer total, with the crosscuts and everything. The TBM portion about roughly 100 kilometers. The project went under up to about 2 kilometers worth of overburden. No matter what rock type you're going through, when you go to 2 kilometer depth, the in situ stresses are high, and with induced stresses added to it, you have to anticipate either rock burst or ground squeezing in most cases. The ground squeezing was actually an issue here. It forced them to change the construction methods from a shielded tunnel to open tunnels. Why? Because they, by design, allowed for huge deformation in the ground. So when you have a TBM that's open machine, it allows you to excavate, and in the back of the machine, you put ground support up. But by design, you're letting the ground to converge, right? And you have to put secondary and tertiary ground support in. In that project, based on what I know, they did a fairly meticulous risk assessment, and they were pretty much ready for a lot of this. And by risk sharing, actually, the owner was willing to pay for it instead of going directly to a claim. I don't know the details of the claim situation, but they had, by design, had to deal with ground squeezing, and selection of the machine and the construction method per section was reflecting that knowledge. They use open TBM by design and allowed for a lot of changes. The next project I want to talk about has also issues with ground squeezing. This was in Iran, Gomrud project. It was total of 50-kilometer tunnel in 5 packages. Package 3 and 4 was actually excavated by the machine that you see here, double shield machine. And the general depth was not all that much. It was 200 to 400 meters, but the rock was weak. It was a schistose rock and fairly weak rock. They actually finished the project. However, they had to deal with a lot of ground squeezing issues. Excavated diameter 4.5 meters, finished diameter 3.8. Started in 2004 and actually took 5 years to finish about 12 kilometers. Originally, 14 kilometers was originally designed, but they ended up going further to about 18, 19 kilometers because the other packages of the project were behind the schedule. So they could actually push through and go to the rendezvous point. This is the geotech, profile of the site, and in particular, if you look at the anticipated radial convergence, which is a squeezing, it gets quite a bit. It gets to the point that it goes beyond the overcut of the tunnel and grabs onto the shield. So they had shield jamming and entrapment. Again, if you look at the chances for ground squeezing, there are several sections along the tunnel that had that possibility. In reality, that's exactly what happened. You see that The ground converged. It came and it touched the shield and they start pushing against the shield to the point that the shield was completely trapped. What you see up here, actually in the back end of the machine, they had to cut the shield by torch and I started releasing the machine manually. Just imagine how horrible that job is. It took them, the first time that they got stuck, it took them 4 to 5 months to release the machine. By releasing machine is like this. You go out of the shield, manually break the rock and put posts, hoping that the ground would hold up. And when you release the machine, you could push against the segment to go forward. Very dangerous, very risky job and time consuming. 5 months, you can imagine the cost of that. So in ground squeezing, this is the situation. You have to anticipate it. And if that is the case, essentially be prepared to go with an open machine, as was the case in Leuchberg. And double shield is a curse there because it gets stuck. They actually released the machine another few months and a couple of kilometers away. As you remember from the geotech investigation, there were several sections with squeezing. They got stuck again. How much they could do to prevent it, if they could actually maintain the machine advanced at the very fast pass, they could pass through the ground squeezing, because squeezing is time-related behavior, right? If you go through it fast, you might be able to get away with it. If you have delays, then the ground comes at you, and when you get stuck, you get stuck. The next project is Zagros Mountain, tunnels. It's a combination of several projects, but this particular lot was a 26 kilometer, 6.7 meter diameter. Double shield machine again. But this double shield machine, remember, it's not pressurized phase. So the water comes in as you go through the formations. The problem was running into gas. So this is the geotechnical profile. The formations here are known, this is in Western Iran, and the formations were known to be the same general formation where they were producing oil and gas. And guess what? Right? Ignored that fact and they ran into it. So you can see these Gurpi and Ilan formations are known to be producing oil and gas. They were expecting that the limestone in the center, oil and gas has already been evaporated and gone, and they didn't really pay attention to going at the depth and sampling. So what happened was they had actually H2S, which is sulfuric sulfide, hydrogen sulfide, and CH4, methane, coming in. Bad news, really bad news. What happened was that they literally had to go and redo the whole damn machine, because the machine was not explosion proof and definitely was not set up to deal with the acidic conditions of the H2S, meaning that a lot of components of the machine had to be hauled out, redone and put back. Some of them had to be repaired in place. And with the H2S and methane presence. So as I will show you, when they encountered the gas first, it was where there was a huge inrush of water coming in. On the right-hand side, you can see the guy is trying to get out of the train, right? And the water is up to their almost waist in the train. So the amount of water coming in was very high. And as the water came in, they essentially, you could see gas is going up. This picture shows the tar that is coming through the joints of the segments. Tar is what? Is a hydrocarbon product coming in. So with tar, you can anticipate gas and other stuff. So if you look at the water ingress into the tunnel and the amount of gases being released and detected, you can see there are sections in 2011 that the amount of gas that was released is even beyond the detector's limit. So the red lines hitting the roof, the ceiling there, that means that there is so much gas. It was beyond the detection limit of the sensors. So what they had to do is to shut down the whole operation. let it drain, then go back with, mask, and I'll show you the picture, and essentially with the oxygen mask and PPE level 4 or D, start dealing with this situation. And ultimately they had to try to capture all of that water as soon as possible, pump it into a pipe, and release it outside so that the gas is not released inside the tunnel. You can see the utilization versus the gas release. When the gas release was high, everybody had to walk out. That's it. So you see the people going in with the PPE level C or D with oxygen tanks in their back and trying to maintain the machine and run the operation. Very difficult, very slow. And unfortunately, in a situation where a couple of the workers ignored the fact that they needed to go in with the PPE, we had two fatalities in that project. So gas is bad news. One of the recent projects was this Omaoyo, which is actually a complex of 2 dams, an interlinking tunnel, a head race to a drop shaft, and the power station and tail race. It's a pretty big project, 1.2 billion in highlands of Sri Lanka. The head race and tail race was actually mined by TBM by double sheet. These are the pictures of the site, fairly rugged mountainside. You can see the job site with the segments. This is the portal of the head race TBM. This is a general picture of the, the whole complex and the caverns. And so what you see here are not swords. These are the pieces of rock coming out of the face. It was so hard at the section that the disc could not cut it. And the cut would not go through between the discs. So it's a fairly messy project in that sense. At the beginning, you see, these are the ridges between the cuts at the face, and they were building up to about probably 3.5 inches, and it wasn't clearing out. So the result was that the discs were wearing at such a rate that was unbelievable, and they were not making progress, 1 or 2 millimeter per revolution, which is actually a big damning situation. This is a picture of the face. This is what was happening to the discs. Rock, when it is abrasive, it is not forgiving. It messes up everything. Look at the center quad being really run out. And you have to go in not only to change the cutters. With this type of damage, you have to change the housing. So there is a lot of welding, cutting involved in that. It is very time consuming. They passed through this section anyway. However, they ran into water, a lot of water. In 2014, they hit a water yielding formation at 1 cubic meter per second. And that is gonna mess you up, right? So they had to stop and actually grout the place and then continue. And in the next zone, they hit another 2 cubic meters per second. To 2015, they hit 4 cubic meters per second water gushing in. You know what that looks like? Let me show you how it looks like. This is what's supposed to be the tunnel with a double track. This is the tunnel with 4 cubic meters of water pulling through. And if that is not enough, and the videos are not coming up, let me see. Right? And let me see. And this was the train ride going up. Not a pleasant, water ride in a tunnel. Caused a lot of social issues as well, because it was literally draining the surface of the water of the creeks, all the wells for farming communities, the death sentence, right? A lot of issues there. Next project is actually under construction now. I don't know whether there is a claim. If I knew it, I wouldn't tell you. This is South Harbor CSO project. And what you can see is the formations and the tunnel alignment going through Hartford Formation, which is a beautiful, nice limestone going through a fault zone where it runs into multiple layers of basalt. and a different limestone there, Bedford or something formation. But look at the profile here, right? A lot of holes, and it shows this particular zone. Again, on both sides, it is fine. It is a good limestone, but in the middle there, it is running into these fault zones. So let me blow up the middle section. See over here, there is all type of faults going through, right? What scared everybody was that in one of these borings, they measured water pressure. Essentially, they started boring water, started gushing out. So it was artisanal pressure, higher pressure, probably being fed from the upper level formations through special channels. A project in Chile for El Teniente, actually, the project was fairly interesting. It's supposed to essentially suck water in from the ocean for water treatment and desalination, and then send the salinated water or the wastewater back into the ocean. And this was the profile. It was so messed up that they chose not to even call it any particular formation. They call it unclassified rock. Well, that's a risk mitigation system. However, the contractor had to deal with it. So these are the situations that could happen. Seattle, one of the university line, metro lines. And what I'm going to show you here is actually, this is soft ground, so it has nothing to do with rock, except for it ran into a boulder. And look at what, this is the job site, right? This is the tunnel and so on. This is the machine pulled out. And this is the machine, what it would look like. And if you pay close attention, around the head, there is a section that's been messed up like here. 1 or 2 boulders can do this much damage to a 6.5 meter diameter machine. So what is boulder? It's a rock, we have to deal with it. But it's in a matrix of soil and it can cause issues. A recent project, 7.6 kilometer built by 2 TBMs by pipe jacking, 2.7 to 3.1 meter diameter, 19 pushes, 19 sections. And what they had to deal with was a lot of boulders. It's funny, if you look at the profile, as I'll show you, there is a section that goes through bedrock. Machines just nailed it, zipped through. But in the section that had alluvial with boulders, problem after problem. So the project went from 880 days anticipated to about double that, about 1,600 days roughly, and huge claim. The boulder strength measured up to 165 MPa, Searcher of 4.7. That is scary, guys. 165 MPa boulders, 4.5. Searcher, that's major stuff. It hits the face, it could really mess it up. So you'd essentially see that here are the borings, right? It shows some rock fragments and boulders. And if you look at the shaft sites, these are the shafts. They go section by section. Some sections indicated a lot of boulders, nothing happened. There are sections that there was no boulders, then the machine had to go through a mess. This is the end of the project at shaft 26. Again, a couple of boulders were anticipated, or few boulders per se, based on the borings, but in reality, machine zipped through it. So this is the picture of the machine and the formation. What you see here going from one shaft to the other shaft, it went through an actual bedrock and it did fine. But the boulders, this is a machine pushing through one of the shafts. Look at the size of the boulders that they had to deal with. And it's not only the shaft, it is probably accumulating probably ahead of the machine and could damage it. So this was a very brief overview of the type of issues that we may run into. Rock strength in the geotechnical baseline report should be realistic and reflect what we should anticipate. Abrasivity could really mess up the operation. You have to pay attention to it. Joints and rock mass. If you overestimate or underestimate, it's going to come back and haunt you. It has to be, to the extent possible, realistic, but you have limited means because you're going through the borings. Groundwater is probably our worst enemy. I've seen, especially in past probably 10 years, Some projects go in totally different direction just because of the groundwater issues, because they don't want to deal with it as a risk, especially in urban areas, because the rock face is stable, the wall is stable, but the water coming through will actually lower the groundwater table, and it would create subsidence at the surface. And that's something that a lot of owners and contractors don't want to deal with. Gases, bad news. So in a lot of geotech investigations, you have to pay special attention to total hydrocarbon measure, TPH. And if there is possibility of gassy ground, you have to be very clear. I mean, all the contracts in LA now, the ground is declared gassy. Why? Because the gas comes in, everything else shuts down. High in-situ stresses should not be ignored. It could be cause for rock burst or squeezing. Both of them are really bad news, right? Both of them are bad news. And selection of the machine for this type of situation is very difficult because you're bound with two different opposing situations where with ground squeezing, you might be able to get away with it with open machine, but if you're going to rock burst, the open machine opens you to rock burst, right? So selection is very difficult. And in some projects, many projects, getting longer, and longer project at high depth means that you have both situations, both the squeezing and rock burst. So you have to do a risk mitigation and metrics to see which one is worse, so be prepared for it. And of course, boulders, which is really going to mess up everybody. So I'm going to just jump through some slides. I wanted to discuss what the geotech mitigation systems are, but I'm going to go just right to the concluding remarks here. But what you see in these slides are primarily different geotech measurements, and actually you can do to try to mitigate some of these risks. So it all comes to risk management, really. You have to look at the geotech investigation information and how much you're spending in testing, investigation, and analysis relative to the overarching risk profile. What you see in this graph is the amount of, let's say, the length of the borings compared to potential claims relative to the bid cost. So the higher number here means bad news, means that it's a construction claim coming in relative to or as a percentage of the bid cost, right? Going out. So let's say for every dollar on the bid, you could face 60, 70% higher number in the actual construction because of the claim, right? So you got to be careful there and don't shortchange the geotech investigation. Do a good job of risk profiling and risk registry. These are some essentially costs of geotech investigation relative to the cost of bid for projects recently. And the higher geotech investigation gives you a better chance. And ultimately, geotech investigation for tunnels is really critical, different than the other construction. It requires a specialized testing and specialized testing depending on the construction method. If you shortchange the investigation, it's going to come back at you as a claim. Site investigation in rock or geomechanic testing plans has to be dovetailed into the risk registry. Don't separate them. It has to be combined. You have to know what the risks are so that you can do the proper investigation. And a word of advice for owners, don't shortchange geotech because the comeback is a bitch. It's going to come back and hunt you. Do it right the first time. Don't shortchange the geotech. Geotech consultants and designers make sure that you educate your client and make sure that properly design your geotech plans relative to the risks. Contractors, they have to actually spend some money to identify the risk ahead of time to avoid claims and bad ground conditions. And for general geotech engineers, be ready. You're going to be blamed one way or the other. At the end of the day, geotech engineers get the short end of it. All right, thanks for your attention. I'll be glad to take your questions.
Let's also try to pull up here questions if there are any that we can. reasonably answer, I guess, within our given time. So I defer to you, to Jamal, to browse through and then try to answer.
Well, they're saying that you're not seeing the videos. Videos are actually on the corner, but the main screen is the presentation. Let's see, how many of these tunneling projects did geophysics? And if they did, what was the very little or lot of geophysics in the right tab? Okay. A question in the chat box about geophysics. If they did geophysics, a lot of these projects do geophysics, but geophysics is not definitive. Again, geophysics, the best it can tell you is rock soil delineation, which is a good piece of information to have. It doesn't help with boulders. It doesn't help with the rock conditions. It just tells you where rock and soil interfaces for the most part. And it also can help with the groundwater issues and where the groundwater table is. One thing about geophysics, I didn't talk about karst or caves or big openings, big voids in the ground. It's a very big danger. Geophysics is very good for that. Actually, it can identify voids and caverns pretty good. So if you anticipate it, like if you're in Croatia or if you're anticipating sinkholes in the ground, like Maryland or Florida, that would be a good choice to look at the potential for sinkholes and voids. But geophysics are done to connect the dots between the borings, but we have to keep in mind that information from geophysics is not definitive. Is there other questions? Let's see. For NYTBM tunneling in schist shown on the slide, what kind of additional rock support system was installed for shear zones? A good question. Actually, in TBMs, typically we don't like shotcrete unless it has been by design put into the backup. Putting shotcretes in the TBM, of course, shotcrete, you cannot do it with the shielded machines anyway. It's a mess. You have to do it afterward. And with the open machines, there are machines that have shotcrete, but they're larger profiles, and it's by design. If at the spur of the moment you want to apply shotcrete in TBM, that's really bad news. It's going to mess up the entire operation. We don't like it. So primarily in the New York tunnels, they went with additional rock bolts with additional wire mesh and steel straps to reinforce it. When the ground gets really bad, you can actually set up steel ribs. Most open type machines allow for steel ribs. Also, most of the good and update machines now, they have capability for probe drilling, meaning that they can drill ahead of the machine and pre-install a spiling or forepoling to prevent ground collapse. These are the measures that you can use in the bad zones. How are we doing with time for the class? Right. So maybe one question from the audience, if anybody here has any questions.
Jamal?
Yes.
Button in here. I couldn't seem to post a question, but you mentioned anisotropy as being a problem on one of your penetration rate claims.
Right.
If you could just speak to what the state of the practice is for determining, for measuring, and for baselining anisotropy with respect to TBM operations?
Thank you. Good question. The question is about anisotropy. A state of the practice is to do perhaps Brazilian tensile strength to see the differentiation between the different directions. Point load is a very good test for that. And it gives you an appreciation of the anisotropy in the rock, and you can actually, relative to the direction of cutting, you can interpret it whether it's impacting the cutting negatively or positively. But drop me a note, and I'll be more than happy to discuss that offline. Apparently, we're running out of time here.
Thank you.
Thank you for the question, and thanks for participation.
All right, so I think with this, we can conclude this session today. I would like to thank everyone for either in-person or virtual presence, and look forward to seeing you in our future webinar series.